He's never led me wrong. And so first, let's invite Ian Cost up. He's from Integrative Anatomy, and his talk will be the flexible heads and crushing bites of parrots.
Cool. All right. Am I good at distance here? Usually the microphones are on podium, so I don't have to hold them. You may have noticed I've kind of taken some of the dinosaurs out, so mostly just parrots today, but we'll talk a little bit about dinosaurs a tiny bit. Like you said, I'm from an integrative anatomy and fifth year PhD student, so this semester I'm writing up most of my stuff, so this is some finished information that I have. But mostly we're just going to keep it fun and talk about birds because birds are fun. First, just get most of the thank yous out of the way. Some of these people are actually here, which is really cool because they get to see their own name on TV, which is awesome. But lots of people have helped me get things and helped me actually build models and do a lot of my work, which is really cool. So, without any further ado, with all of my thanks and everything, how many people here have a skull? Oh, thank God. I thought it was going to be very mixed. So the human skull has a brain case, to start off with that. It's made up of these bones and a couple of the internal bones that you can't really see too well. But we also have a mandible, which is what's flapping up and down here as I talk. A maxilla, which is right below your nose. A palatine, which if you put your tongue into the roof of your mouth, you can actually touch your palatine. And a pterygoid shelf, which is part of the sphenoid, which is part of the brain case. You can't touch that, I hope, because it's internal. But all of these things are going to come up later, which is why I'm starting off by showing you the human skull. Don't worry, we're talking about birds right now. So, birds are a very diverse group. You've got birds that swim, birds that fly, birds that dive, birds that swim with their feet, birds that swim with their flippers and wings. We've also got birds that walk, birds that don't have feet so they can't walk. We've got all kinds of different birds. And you can appreciate the different faces here, the different sizes of legs, talons, all sorts of different things going on with birds. But the thing that I look at most is the head. So if you're just looking at this, you might not know exactly what I'm looking at, but any ideas what I might be looking at here after I said the head? Go ahead and shout anything out if you got an idea. Some movement. So in particular, if you're not seeing the movement I'm talking about, you're looking right about there, actually. And you can see that beak going up and down, and we're gonna go over that a little bit, not in too much detail, but it's a very interesting part of how birds eat, and that's something that I'm very interested in and do a lot of work with. So if we look at a generalized bird, chicken is a pretty generalized bird. It's got some of the same bones that we've got, except it's fusing up its brain case, the first thing you notice. We had all those individual bones, and we have sutures in between. But birds are fusing that up. They also have a maxilla and a mandible, just like we do, except they turn those into a keratinized beak. So the same thing that your fingernails have, they're covering those bones with that, and that's what a beak is made out of. They also have this interesting thing. I put this up because it's interesting, not because we have it. The sclerotic ring. It's a ring of bone around the eye within the orbit. They also have a craniofacial hinge, which we'll come back to a little bit later, but you did see some movement at that hinge already. And then they have some other bones that I mentioned earlier that we have, the palatine and the pterygoid. And they form those into a thing called a palate, which you have as well. If you put your tongue in the roof of your mouth earlier, you felt your palate. You have a hard palate. Birds do not have a hard palate. They actually have an open palate, so their nose is connected to their mouth. So when they breathe in through their nose, they're actually breathing straight into their mouth through their nose. Now, no matter what birds look like, all of that head anatomy is basically the same. There are obviously some derivative animals, like the toucan up there with his big beak. We're on TV, so that's a little hard to point. And the hummingbird over here. Anhingas are really cool. This is bird with the long neck here. All the same anatomy in the head, but very different heads. You can appreciate that looking at just this small swath of birds. So why with all of that would I study parrots when we've got all of that different diversity? Part of the reason is they're very vibrant and beautiful. Everybody loves parrots. That's why they're big in the pet trade. That's why they're big in zoos. That's why they show up everywhere. Additionally, within species, you can have multiple different colors. So these are budgies down here in the corner. That's your typical pet store bird. You go to PetSmart and you see like 15 different colors of budgies. They also love high school yearbook photos. Sometimes they're just green. That's okay too. They definitely have different personalities. You can tell looking at all these birds that they have different things going on. They're very intelligent, which has enamored people in psychology as well as the pet trade again. Pet trade is huge for parrots. We keep coming back to that. And they're also a very big part of conservation in general. So this bird down here is the kakapo. There's about 145-ish left right now, and they live on like 3 islands in New Zealand. And those islands are like, totally off limits to everybody. Additionally, they have a big size difference. So on your left is the hyacinth macaw. It's about 4-pound bird, 3 feet long from the tip of its tail to its beak. And then on the right is a pygmy. It's a buff-faced pygmy parrot. It's about ½ an ounce in weight and 3.4 inches long. So if I make it about the right size compared to that hyacinth macaw, you're looking at this much difference. So it's a considerable size range. Additionally, parrots are pretty global, which is really cool. They're found on almost every continent naturally, and they have a variety of different bodies within those continents. But overall, their head shape stays the same, as you can see from all these skulls on this map, which is really cool and part of the reason that I'm studying parrots, because I'm looking at how the head works, and I'm taking these animals that are global and looking at how a very similar head eats different things, and I'll show you what they eat in a second. Important to note here, North America, specifically the United States, used to have a natural parrot, the Carolina parakeet. That parrot was hunted to extinction by us, for the most part. Now, what's that?
I said, no way.
Oh yeah, totally. Deforestation was a big part of that. And now any parrots you happen to see in the United States are typically escaped animals from the pet trade. So you don't actually have a native parrot anymore, unfortunately. So as I said, they have a very diverse diet. We have parrots that eat seeds, leaves. We even have specialized parrots, like the lorikeet down there, that eat nectar only. It has a very specialized tongue, which I'm not looking at, but it's very interesting. It's shaped like a brush. And then up in that right-hand corner, you see that's a hoof. There are parrots that will eat meat. Some of the parrots that eat meat specifically go for things like bugs and insects during the breeding season when they need proteins. That's a Kia. It will attack livestock to get at kidney fat. So it actually does have active carnivorous instincts in it. Well, it's from New Zealand, so it wasn't originally attacking sheep because there weren't originally sheep there, but it does now, and farmers don't like it. So just to go over some of the diets of these parrots that I'm looking at. A lot of them eat grains, a lot of them eat fruits, and a lot of them will take veggies, any kind of vegetable they can get to. The Kia will go after meat, as I said. And then this is the kakapo I mentioned earlier, very specialized, very high conservation efforts with this parrot. It eats leaves mostly. It eats fruits during the breeding season, but most of its diet is leaves. So what do animals that eat mainly leaves mainly look like? Think of the animals in your world that eat mainly grasses. What kind of animals are you thinking of?
Cows.
Cows, elephants, giraffes. So the kakapo has to be bigger than other parrots, so it's the only flightless parrot. So not only is it down to 147 individuals that live on an island, it can't fly away from things that try to eat it. It in fact actually has to use its face as a hook to climb. So very weird. The Carolina parakeet, we don't actually know exactly what it ate because we went ahead and killed it off before we got really good science on it. as we do. So part of my work has been to rebuild all of these animals and determine if we can tell what they ate by the way their skull is built. So that's why I have a Carolina parakeet, because we have an extinct parrot, and we want to know if its skull is built the same way as the other animals that eat those things. So when we look at the excuse me, when I look at the anatomy of a parrot, we're looking at a bird, and you can appreciate that it looks very bird-like. It has a fused brain case again. It also has that craniofacial hinge. In these guys, it's super well built, such that there's only a tiny little spur of bone between its beak and its brain case. And that allows it to be what we call hypermobile. So it acts like a door hinge when you go to open a door, except the door and the wall would be the beak and the brain case. So it's got a lot of movement there. Some of them have this suborbital arch, so you might see on some of my CT scans that I show this ring of bone that goes below the orbit. That doesn't show up in every parrot. We don't know why it shows up in some. We don't know why it doesn't show up in other ones. Sometimes there's a muscle there, sometimes there's not. It's an interesting thing, but we're not going to get into it today. And they also have this kinetic palate. Remember I told you the palate was going to come back up? So they have a quadrate, a palatine, and a pterygoid, and those act as the engine to move that hinge. So the quadrate has muscles on it that are acting like the engine of like a forklift. The pterygoid is acting like a mechanical strut, and then the palatine will act as the actual lift. So that will actually lift the load, which is the beak, the maxilla at the craniofacial hinge. Just to bring it back to you so that you can think about this in terms of humans, we still have a quadrate, but it's not in the same place. Their quadrate is at the jaw joint, so it's right in here. Our quadrate is now in our ear, and it's the incus. Interesting tidbit, the malleus is the articular bone that makes up the jaw joint with the quadrate. So our jaw joint, if we were birds, is now in our ear. It has moved through evolution. The palatine, like I said, is in the roof of the mouth, and that pterygoid shelf, just to remind you, is a shelf of bone inside the head where you cannot actually reach it. But we do have all of these bones still, just in a different orientation. So now down to the actual brass tacks of what I'm doing here. We take the software that's like this for building engineering structures, bridges in particular. And what I do is I rebuild birds as if they are a bridge. So I take CT scans of these X parrots, and I put them into the computer. And I put little muscles on the X parrot models, which simulate what that truck is doing, putting a load on top of my bridge, my bird. And then I can actually build in joints and actually fire off all those muscles and get the bird to do what it would be doing in real life, actually biting, but in a computer. We also put in places that the bones can't move. So just like that bridge, you have anchor points on either side so that we get some movement that's determined by the forces, just like in this bridge. So 2 anchor points, and then the muscles are the truck going over the bridge, and the bridge itself would be the bird. But just to really quickly go over the quantities that I'm looking at, stress can be found in 2 different flavors, compression and tension. So compression, if you push the spring up, if it wants to work, there it goes. And tension, where you're pulling that spring away from that board. And one of the qualities that I look at a lot is strain, which is the change in the material itself. It's actually looking at the difference between the uncompressed or untensed spring and the compressed or tensed spring. So you're actually looking at how things deform when forces are pushed into them or pulled on them. And there are 2 flavors of that also. Elastic deformation, which means it's reversible, which my favorite example is hockey, because the stick starts out straight, and as you watch this, when he makes contact with the puck, you'll see that it actually elastically deforms the stick, you get a nice curvature, and then it will go back to being a stick. The opposite of that is plastic deformation, which is an irreversible change in that stick. So irreversibly changing it, it's not going to just bend back, right? What's it going to do? It's going to break somewhere. He happens to put enough pressure, force on the stick that it breaks right below his hand. So those are very good slow motion cases of elastic and plastic deformation. You can find lots of those on the internet. People love hockey sticks. It's great. So when I actually get that truck over my bird bridge, we generate all of these little maps. These little maps show us the actual deformation in the materials that we are working with. So here's all my little bird bridges that have had trucks driven through them, and you can see the different colors in there. What the colors mean are how much of a deformity that the material is under. So red spots are a lot of deformity, blue spots are none or very little. White spots are actually structural failure. And what happens when they get to white is either the bone is going to bend until it breaks or twist until it breaks, or with parrots, that bone will actually push the next bone, because that's the pterygoid that I've got highlighted there. It actually pushes the palatine. Remember, that's the forklift arm. And then the palatine will move the beak. And then, of course, we care about the middle of the road strain values as well, because those are telling us that there are forces there, but it's not breaking. So the bone is withstanding those forces or transmitting them accurately or well enough that they don't break. So when I look at all of these, I can actually pick out some patterns. And most of the patterns that I've seen are within this otic process of the quadrate, which is really cool because the otic process of the quadrate is the arm upon which the quadrate rotates the head. An articulation with the limb itself, and it's a ball and socket joint. So if there's actually forces in here, that means that the quadrate's trying to twist in that area. So when we put the forces on there, that means that that quadrate's trying to crank the whole system forward, and it's getting lots of forces in that arm. And then the other good place that we see a lot are in the pterygoid, in this long bone here, and the palatine, which are those parts of the forklift system that I said push that beak up. And it's looking at it statically, it's interesting, but it's not anywhere near as interesting as if I and actually put it in motion for you. So this is the kakapo skull. This is that endangered New Zealand parrot. And I've left the mandible on here, and you can see that when we fire the muscles, there are parts that light up, there are parts that don't light up as much, but those muscles are closing the jaw, which thankfully we expect it to do because they're pulling on the jaw. So they're actually closing that mandible, and they're trying to move the palate at the same time. If I take that mandible off, what do you think happens to the rest of the skull? Any guesses? That's fair. So if I take the mandible off, we now don't have that arm moving. Instead, we see that otic process that I was showing you right here, lighting up because it's trying to twist the quadrate. So it's trying to crank that whole forklift arm forward. Now, it's a little bit opposite of that video I showed you at the beginning, but if you look right there, that's the craniofacial hinge. So what's everything to the right of that doing? Everything to the right of it is moving, and everything to the left is not, right? In that video I showed you, everything in the skull of that first parrot was not moving, but this was. So if I got that to not move and this to move, it would be the exact same thing. So we've recreated, or I've recreated, the actual movement of that parrot eating in a computer model right here for you, which I find really cool. So thank all of these places that have helped me scan things. And then just to prove that bird box is really, really bad, if you put a parrot in a box, it does this to it. Parrots love boxes. And if you can look really close up, you can actually see that whole craniofacial hinge moving and the scissoring action that it's creating. Oh, this goes on for like 5 minutes and this parrot destroyed this box. It loves it. But it's got lots and lots of movement in there. It's just a scissor on the front of its face, basically, which is really cool. If you guys want to keep watching this. If not, and I have time, I can answer questions for you guys.
How many degrees does the cranial facial hinge move?
I haven't actually measured it, but the models that I've made, I have moved that quadrate 5 degrees. So if I go back to where this was moving, I moved that quadrate, I've moved it 5 degrees to simulate motion. And the entire system downfield has moved 20 to 25 degrees because of that. So it's a very appreciable, you can definitely see it in those videos, and you can definitely see it when you move those bones even 2 or 3 centimeters. So it's got a wide range. Yes.
Has this given you a clue as to what the skulls of the extinct Carolina ate?
Yeah, so I have, oh yeah. The question was, has this given me any insight into the Carolina parakeet and what its skull is doing? It's given me some, but the general idea that I've gotten from it is that even though I see some of those patterns showing up repeatedly, that I need a lot more data from a lot more parrots that eat similar things, because they're so omnivorous that it could be a number of things that are causing it. But basically, I've been able to say that Carolina parakeets could have definitely eaten the same things as like a gray parrot, but I can't say 100% that that's definitely definitively right now, because I don't have enough background data for it. Yes, sir.
So, parrots or birds are closely related to dinosaurs, right?
Yes.
How does the skulls and machinations compare to other archosaurs or even crocodiles?
So crocodilians, whenever I've actually modeled a Tyrannosaurus and looked at how Tyrannosaurus's head does not move like this because it's built up too well. It has a lot of bracing features like that act basically as like the trusses of a bridge. So it does not move when it bites at 65,000 newtons of force, because that movement would actually break its skull. So it doesn't have any kind of kinesis. But I use alligators as the other side of the bracket. So I put parrots on one side to show me what lots and lots of movement is. And then I actually used a tokay gecko because it has a different kind of movement, but we put alligators in there also to see what no movement is supposed to look like. And then because it goes, if you look at the family tree, it goes geckos, alligators, dinosaurs, birds. We can kind of figure out where they should be on that spectrum. But yeah, when I fired a Tyrannosaurus Rex, it did nothing like this at all. It actually started to break at a lot less range of motion. Yes?
I understand hyenas have an enormously powerful bite. Do you model them?
No, mammals are a totally different animal. So the reason I didn't model hyenas at all is because they're built like the rest of us. And when you look at that, they have a totally different skull going on, and they actually fuse up a lot more of those sutures than we do. So they're actually, I don't want to say just like alligators, but their skulls are built a little bit more like alligators than ours are, in that they don't move so that they can build the forces up to crush bones and that sort of thing. These guys instead use manipulations of their beak to break things open and crush things, and they generate high bite forces even with a squishy skull that way. Cool. Thank you.
Thank you.
That was a great talk. We'll take a short